Resistors are connected in parallel when both of their terminals are connected to each terminal of another resistor, as shown here. The combined total resistance of parallel resistors will be less than the resistance of any individual resistor because the parallel configuration provides more possible paths for electrons to take as they travel through this circuit. When thinking about why combining resistors in parallel affects resistance, I like to use the analogy of current passing through a resistor being like cars traveling down a road. Adding a second resistor in parallel creates a second possible path for the cars to travel down. The resistance along each path corresponds to how difficult it is for the cars to drive along it, with a larger resistance representing a more treacherous road. If both roads have the same resistance, the current traveling through them will be split equally among each path. Half of the drivers will choose to go down the left side, and half will choose to go down the right side. Conceptually, this doubles the width of the road, which makes it twice as easy for cars to travel down it. That means the overall resistance of this two-lane road is half what it was as a single lane. If each of these lanes had an individual resistance of 10 kiloohms, their combined resistance in parallel would be 5 kiloohms. Continuing down that train of thought, combining 3 equal resistors in parallel creates a 3-lane road, so its total resistance is 1/3 of the resistance of a single lane. When you combine multiple resistors in parallel that all have the same individual resistance, you can calculate their total resistance by simply dividing that individual resistance value by the number of resistors. Remember that this only works when all of the resistors have the same resistance. When you combine multiple resistors in parallel with different resistor values, things get a little bit trickier. Consider these two resistors in parallel with different values. Using the road analogy, the 10 kiloohm resistor on the left represents a road with some obstacle on it, perhaps some potholes. That means we can treat the 20 kiloohm resistor on the right like a road with twice as many potholes. So it's twice as difficult to drive down the 20 kiloohm road as the 10 kiloohm road. The current will be divided among the possible paths based on their relative difficulty. So in this scenario, twice as many drivers will choose to go down the left path than the right path, because 10 kiloohms is half the resistance of 20 kiloohms. To calculate the combined resistance of these two resistors, I can use this equation, which says that the inverse of the total resistance is equal to the sum of the individual inverse resistances. This is a handy equation because it can be expanded to combine as many resistors as you want in parallel. So, for my 2 resistor example, I'll need to calculate the values of 1/10 kiloohms and 1/20 kiloohms, which are 0.0001 and 0.00005 ohms respectively. Added together, I get 0.00015 ohms. That value represents 1 over the total resistance. So to get R total, I can manipulate this equation by flipping both sides. That gives me a final answer that the total resistance of a 10 kiloohm resistor and a 20 kiloohm resistor in parallel should be about 6.66 kiloohms. The best way to check my math is to actually measure the resistance of these two resistors in parallel using my DMM. I've placed a 10 kiloohm resistor in parallel with a 20 kiloohm resistance on my breadboard, and since 20 kiloohms is not a standard resistor value, I've combined 2 10 kiloohm resistors in series to create that 20 kiloohm resistance. When I measure these resistors with my DMM, I see that the total resistance across them is around 6.6 kiloohms. If I connect these parallel resistors to a 5-volt source, according to Ohm's law, their effective total resistance of 6.66 kiloohms should draw a total of 0.75 milliamps of current. Using the equation of power equals current times voltage, that means the combined resistors will dissipate 3.75 milliwatts. Using Ohm's law to individually calculate the current through each resistor, I see that the current through the 10 kiloohm resistor on the left will be 0.5 milliamps, and the 20 kiloohm resistor on the right will get 0.25 milliamps of current through it. These two current values add up to the total combined current of 0.75 milliamps, which is the same value I calculated a moment ago. But as you can see, the current is distributed unequally among the resistors based on their values. Similarly, the power dissipated individually by the left resistor and the right resistor will be 2.5 and 1.25 milliwatts respectively, which add up to that total power of 3.75 milliwatts that I calculated earlier.